Welcome back, everyone. Let's go ahead and get started with our afternoon session. So our first speaker, I think very synergistic with a lot of the previous talks, is going to be Grant Rotskoff from Stanford.
Okay, thanks. So I want to start with something that's like a parable, maybe. So this is a plot. I want to open it to the audience to guess what this is a plot of. So you can tell that the x-axis is time, and this is the COVID-19 pandemic. Any guesses? So that's a good guess. It's something that's very strongly correlated with the stock market. So I was a PhD student here. I sat right down the hall right down the road in Gilman Hall. And during my time here, at the end of my PhD, I basically finished my thesis. My advisor was on sabbatical, and I spent essentially all of my time in this room at this program on the foundations of machine learning. And at the time, the thing that everyone was concerned about was self-driving cars, because we were facing the societal problem of what we will do when there are no truck drivers left. So this is the number of truck drivers as a function of time. And the other thing that was sort of funny about it is that also at the time, it was not on anyone's radar that the progress in natural language processing that has been made would be made. There was, I think, one natural language processing talk by Chris Manning at the time, and it was like a bit of an eccentricity, like, oh, there's this other problem that exists beyond vision. And I think that this is sort of like a lesson that we are often much closer to the like 99% solutions than we think. And we're often much farther from the 100% solutions than we think. And this is Berkeley. So to paraphrase the Grateful Dead, we're still trucking. If you're really a connoisseur of the Grateful Dead, you'll know that they actually formed in Menlo Park, which is closer to where I am now. So I'm at Stanford. I'm Grant. And what I want to talk about is something where I think a 99% solution is still kind of far. And that's sampling conformational ensembles of proteins. So we've seen a lot of nice protein structures already today. This is a less nice one. So this is a intrinsically disordered protein ensemble. This is sort of typical of the fluctuations that we might see. And I'm going to tell you about work that we've been doing in my group for the last couple of years, primarily led by Shriram, who's totally amazing, a totally amazing graduate student in my group, and also more recently with Stephen Dunn and Sebastian, who are over there in the room, and Abby and David. So the basic premise of the problem that we are facing is that disorder is something that's very hard to build experimental data sets for. So when we look at a conformational ensemble of a lot of biologically relevant proteins, about 45% of the proteome is intrinsically disordered. It actually is sampling a very diverse set of conformations. So that's something that there are only sort of weak measurements for. We can't directly predict these structural ensembles in any sort of precise way, the way that we can with X-ray crystallography. But the fluctuations in these intrinsically disordered proteins are very important for all sorts of different applications, including therapies. But just understanding the structure of them is an intrinsically interesting problem, one that informs a lot of the properties of aggregates of these materials as well. And so this is something that we need to do. And it's sort of an invitation for physics-based models because there's not really this like broad data set that we can leverage to do just purely data-driven prediction. The other problem with these sorts of systems, though, is one that is called metastability, or in the rare events community, rare event. And this is essentially the observation that biological timescales are long relative to what we can simulate with physics-based models. So this is showing, a sort of separate thread of work in my group, working on rare events methodology with my student Andy. And it's just showing you that the rate for a very simple biomolecular transition is, hundreds of nanoseconds. Is a very, very small basic protein. And that's, probably longer than we would typically want to simulate. And the reason is that we're waiting essentially all of the time to visit these rare interfaces, which are statistically rare under a Boltzmann distribution. And that's the thing that actually drives the dynamical events that are important. So if we want to discover these metastable states with molecular simulation, we would have to basically figure out a way of realizing these extremely rare events. So we saw yesterday that you can do molecular dynamic simulation of something as big as the HIV capsid. And that's a pretty amazing scaling feat. But the biological utility of that, I think, is much more questionable because the types of biological events that we're typically interested in have mean first passage times that are much longer than we could ever hope to simulate. So this is not a problem of GPUs. I mean, we're 15 orders of magnitude away from being able to do this with MD simulation. So a natural question in this context is one that has already been posed a couple times today, which is, can we replace molecular dynamics with something that resembles generative AI? So there are there's a series of papers in the Journal of Protein Structure Prediction, Nature, and so they all have really strong similarities in the architecture, and they're doing truly amazing things, right? I mean, they've really made incredible advances on protein structure prediction. But when we talk about dynamics and dynamical fluctuations, we mean something a bit stronger than that, right? We want more information than what is the likeliest crystal structure for a given sequence. And in order to sort of replace molecular dynamics with something like a diffusion model, I think we can formulate the question very precisely. I mean, we know what we would want to do. We would need to represent a very, very high dimensional probability distribution. So this is the distribution over the coordinate space, or maybe the internal coordinates of a protein. And the objective function is also a straightforward one. We want to sample a Boltzmann distribution. There's a well-defined statistical distribution at a fixed temperature that we would want to draw samples from, ideally in a mostly uncorrelated fashion. The goal of that would be to compute observable properties of the ensemble, right? To compute averages or fluctuations, and that's something that ideally we would do faster than we could with molecular dynamics. Right? We want to accelerate convergence if we actually carry out this task. So one thing that has also come up a little bit today is like, well, what is this energy function that we would actually use? And what I'm going to tell you about, we're going to use molecular dynamics force fields as the energy functions. There are problems with those. I think they're well-known problems with them, but they're actually pretty good. I mean, they generalize fairly well across lots of different types of proteins. They're sort of system-specific variants of the force fields for intrinsically disordered peptides. We use that a lot. And so those generalize reasonably well to experimental data, and we're confident in their ability to generalize. Much more confident than we are about diffusion models, though. So if we wanted to do this, we have to ask some questions about the properties of diffusion models in the context of a sampling problem like this. So diffusion models are already representing a high-dimensional probability distribution. That is what they do. But how close is it to a Boltzmann distribution? So I don't have an answer to that, but there is a sort of separate line of inquiry in the computer vision community that I think sheds a lot of light on the nature of the landscapes of diffusion models. So the basic picture here is that when you build a diffusion model, what you're typically parameterizing is a score function. That score function can be viewed as the gradient of some potential at time zero. If this is a Boltzmann distributed type of problem, right, then we would expect that if we truly converged, then the distribution that we're representing would have a potential energy which is the integral of the score function. So we know one thing about diffusion models, which is that they tend, especially when over-parameterized, to converge to distributions that essentially will duplicate the data set. I mean, they'll concentrate the statistics very much around the samples that have been trained on. So this is something that doesn't appear to be much of a practical problem for images, but it is a practical problem for the sort of naturally kind of variant landscapes of things like molecules and proteins. It's a very different type of of distribution than the ones that we would encounter in images. And then there's another point that I like to make separately, which is just to think about the actual statistical problem of trying to approximate a probability distribution in high dimensions. And so this is a generic result from non-parametric regression. It's a textbook result, actually. So if you go to this textbook, Introduction to Non-Parametric Estimation, you can find it. And basically what it says is that the asymptotic lower bound for the approximation rate, so this is the risk function, so how much error you're making, when you approximate a density function f with something in a parametric class, so f hat. So this has nothing to do with machine learning per se. It doesn't matter how good your model is or how bad your model is. This is just saying among all functions, given some set of data, how close can I get? So the answer is it depends on the smoothness of the target distribution. If the target distribution is very, very smooth, it basically performs like Monte Carlo. It decays like n to the -1. You increase the data set by a factor of 10, you see about a factor of 10 improvement. When the dimensionality is high and the landscape is rugged, you see a different type of scaling, which is more like the curse of dimensionality, n to the -1 over d. So as the dimensionality gets high, the rate of this lower bound is changing very, very slowly. So that's a sort of bad situation. And the classic picture of protein free energy landscapes is something more like this. It is a kind of rugged distribution. And that's something that I think we should be concerned about. But I think it's also something that we all know, which is that we need a lot of data if we're going to do this well. That's something that I think that is no surprise. And one of the things that I want to sort of think about in this talk is how you simultaneously decrease both the dimensionality and increase the smoothness, or increase the data set size. I'm not going to really focus on smoothness. I'm going to focus on number of data points and dimensionality. And the basic premise is that if we want to do this, we need to somehow break up the problem. So we need to build kind of modular pieces of data that we can train on and really exploit this sort of scaling. Okay, so that's mostly the context. And just to say this, the data physics trade-off that we see, so physics generalizes very well, data generalizes well when there's enough of it. This is something that sort of permeates through all of the research that we do, including on things that are very, very small, like reactive biomolecular processes, things that are very macroscopic, like non-equilibrium dynamics, and conformational sampling, which is what I'll focus on today. Okay, so many of you will probably have heard of this idea of Boltzmann generators, and I just want to tell you about some of the generic challenges with them. So Boltzmann generators is there's a paper in 2018 by Frank Noe's group, and basically what it proposed doing was using normalizing flows to approximate the Boltzmann distribution directly from either just an energy function or also from data. And you can do this basically with any type of generative model that we commonly use now. So any of these like continuous state space transformations, like continuous normalizing flow, conditional normalizing flow, denoising diffusion models. So when I say continuous normalizing flow, you should also think that I mean flow matching. These are sort of the same, but trained in slightly different ways. And in this context, the attractive piece is that there are sort of two different ways that we can train models in this class. We can either train them with an energy-based objective, which is just a KL divergence where we look at the deviation from the equilibrium distribution. What's sort of beautiful about this and very, very attractive is that it doesn't require any samples from the equilibrium distribution. This expectation is one that we can compute purely in terms of the model and the target energy function. The second is what is commonly done with diffusion models, not using this objective exactly, but if you were to use a continuous normalizing flow, this is what you would do. You evaluate the KL divergence, which is not symmetrical, in the reverse direction. You use samples from the equilibrium distribution to compute an average of this log ratio of the probabilities. And you get something which basically tries to do likelihood, log likelihood maximization on the equilibrium distribution. So I'm going to show you on a very, very simple example how these two objectives perform. Okay, so here's the problem. We have a double well potential, essentially. So it's a multimodal Gaussian in 2 dimensions. You can see the marginals on the axis. So there's one distribution, there's one mode of this distribution that has slightly more mass than the other. And this is training purely on the energy. So I'm going to initialize a normalizing flow at the origin, and I'm going to watch it evolve as it tries to match this target distribution, training on this objective. So what happens? Anyone? Have any guesses what happens? We learn the distribution. It's mode seeking. It's going to collapse. So it collapses on one of the modes, and the answer that we get is incorrect. So we obtain an incorrect answer, and that's a problem with the objective. It is not a problem with the models. This is something that happens with transformers and large language models. If you train on mode seeking objectives, you mode collapse. So that's an issue, and it's one that's very discouraging for trying to use normalizing flows to do Boltzmann sampling, because actually the thing that we typically care about most is capturing the modes. We want to get all of the modes. We don't want this to just concentrate on whatever low energy mode it happens to find first. Database training, I'm not even going to show you the training video because it just works. Like it does amazingly well. This is sort of an artifact of the normalizing flow parameterization where there's this like thin tube of probability. But if you use this for Monte Carlo sampling, what you see is that it mixes very quickly and the samples converge to the correct target distribution, much faster than if you were to just run Langevin starting, so if you were to run MD starting in one of these wells, the time to cross to the other well would be very, very long, would be exponential. And so this is something that can massively accelerate convergence to the equilibrium distribution, but you need this a priori information about all of the states. Yeah?
Instead of these two? Like, why don't you get one that's kind of like at the same x1, but at the other x?
Oh, so these are the marginals. It's just integrating out the x-axis and the y-axis. So the target distribution is this diagonal thing. Yeah. So it's just looking at a projection along the y and projection along the x. Okay, so this is not an issue with Langevin. If you were to run Langevin dynamics long enough, you would actually find both of the modes. And so part of the question that we're asking implicitly here is, can we figure out a way to do mode discovery in a targeted way? So at a very high level, the goal is to build generative models which use less data, assuming that we don't have all of the modes, and have a bit more physics. And I'll be precise about what I mean by that. Yeah. Yeah.
The idea between these sort of, forgot the name, energy models, like, I forgot the name that you...
Energy-based, or, yeah.
Or like kind of approximating these models posteriors with normalizing flows, the idea that basically the energy has the interpretation of the log joint distribution, then you do variational inference with normalizing flows.
So this problem maps on to variational inference exactly. And if you were to do variational inference with normalizing flows, you have exactly the same set of problems, and you, again, need to know the modes. So actually, with Mary Lou, we have a paper on variational inference for that sort of problem. And yeah, the basic remedy to make normalizing flows work in any of these contexts is know the modes.
Yeah. And another comment, which might perhaps be interesting for this community, there's a paper by Matt Hoffman at Google that compensates for poor geometry in sampling using normalizing flows. So basically, you train a normalizing flow model, and then you map your sampling problem into another space, which is better conditioned. And then maybe that would actually help.
Yeah, I think there are a lot of like really interesting applications of normalizing flows in contexts that look like that, like preconditioning or things where you really need them to not do too much work. And that's what I'm going to sort of transition to, which is how to make normalizing flows do less work. Okay, so the basic premise of what we're going to do is we're going to use coarse-grained models, physics-based coarse-grained models as a latent space, essentially for normalizing flows. And so the basic structure of our first attempt at a setting that looks sort of like this is to start with a fine-grained model, so an atomistic simulation of a protein, to map it down to some low-dimensional subspace. This could be a linear mapping or a nonlinear one. Primarily, we use linear, and I think in the second half of the talk, we're only using linear. And we then run dynamics in a reduced dimensionality space, so one where the dynamics is much faster and mixes faster, so we can explore all of the mode structure. But then we use a conditional normalizing flow to backmap from the coarse-grained space to a fine-grained space. And the point of that backmapping is to recover all of the atomistic configurations, but do so in a way where they can exploit the coarse-grained search over the modes. Yeah.
Is that data-driven in general, or?
Yes. So we took a sort of maximalist approach on this, and so all of these objects that you see are learned. So we learn the mapping operator, we learn the coarse grain potential. So this is just the log likelihood of the coarse grain distribution. And we learn this backmapping operator. So we did a lot of exploration of learning the mapping operator, and we didn't really find that it added all that much. So primarily, we now avoid that. So we used models that we thought were good. So we use an E of n GNN for the U hat. We use a graph autoencoder with something called differentiable pooling to do the actual coarse graining. And then for the backmapping part, we use a conditional normalizing flow. And as it says, I don't think that the specific models are particularly important. You can sort of choose whatever you think is best. Except the backmapping has to be done carefully, because the one thing that we really insist on in this framework is that you can compute the likelihood of the samples that you generate so that we can metropolize them. So I'm interested in sampling Boltzmann distributions, and we really want to be able to compute the generation probability of our samples so that we can treat this sampling procedure as a true Markov chain and actually obtain samples that are distributed according to the correct distribution. Correct up to the resolution of our energy function. So this actually ends up being fairly straightforward from the normalizing flow perspective, because once we have integrated out all of these sidechain degrees of freedom, reconstructing them with a normalizing flow requires sort of less work from the normalizing flow. We can train over configurations of lots of different sidechain conformations, and we can push them back to the fine-grained space. We use rational quadratic splines here. And then we can actually write down the marginal distribution, and we can metropolize in a Markov chain. And so this gives us a quantitatively accurate description of the statistics compared to MD. So we can actually recover the energy distribution exactly. We can sample the sidechain fluctuations fairly well. Of course, what I'm saying requires training all of these models, right? So we have these 3 different objects, and the way that we do this is through a sort of self-consistent training that does require MD from this particular protein. And that is one aspect of this that we would like to avoid. And so I'm going to tell you about how we're thinking about avoiding that now. So what we would like to be able to do is actually backmap arbitrary proteins, in particular intrinsically disordered proteins, and be able to compute conformational statistics of them using our coarse grain models and then backmapping to the fine grained space. Yeah.
Problem?
Why?
Well, because you could have one-to-many configurations.
So these are representing, the models here are representing conditional probability distributions. There's nothing ill-conditioned about it. I mean, it is, it's a probability distribution conditioned on some particular backbone structure, but that probability distribution is perfectly well-defined. And, we're just trying to represent that. So it's not one function that we use. We're using a generative model. So, it's like anything that samples a probability distribution.
Question?
Yeah.
Regarding your coarse graining, for the differential pooling, do you have to pre-specify how many coarse and points you want, or can that be dynamic?
So we do specify the dimension. We include in, so actually engineering the loss function for the mapping operator is the hardest part. And we basically try to enforce sparsity. And so we try to, we try to kind of learn it approximately, and then we can reduce if we need to. But in everything else, I'm going to tell you, we just linearly project to the backbone, because we found that solution is competitive with anything else we've tried. I think that there are probably more complex strategies that we could attempt, but I'm not sure we really have the bandwidth to investigate this. I mean, maybe someone with many more GPUs than we have can try. Yeah.
So in this coarse grain world, what solves this mode seeking problem?
So in the coarse grain space, we can just do conventional dynamical sampling. So we're doing Langevin. We can do like temperature accelerated Langevin. So it's basically just the standard MD sampling tricks. It's just that everything happens faster. So when we reduce the dimensionality, the sampling problem becomes much easier for the mode discovery. And the other thing is that, because the coarse grain spaces, the representations that we're using for the latent space, are incorporating a lot of physical information from the original ensemble, those we contend will generalize better than just an arbitrary latent space, like something that you might get from an autoencoder.
When I misunderstood. I thought in this coarse grain space, you also have effectively a normalizing flow, which is like a generative model.
No. So in the coarse grain space, we sample using Langevin dynamics or any conventional Monte Carlo method on this energy function. So we just run dynamics on U hat, and then we back map with a normalizing flow. So we go from the coarse grain space to the fine grain space with a normalizing flow. Yeah.
So I'm sure you're going to talk about this. There's some assumption about the smoothness of this force matching GNN, what the phenomenon is trying to model.
Yeah. So, well, okay. So, I mean, maybe Tess and Aditi can weigh in on this more than I can. So, U hat is, a neural network. We've primarily used equivariant neural networks, and we're trying. So, these potentials of mean force, they are smooth. They're marginals essentially of the original free energy. So, we know, like, under reasonable assumptions on the potential energy, we know about their smoothness. I mean, they have singularities if you were to, like, put points close together, but.
So I'm going to ask a question, like, how can you use this process, based on your description, to discover that thin manifold of the dynamics you care about, that you motivated at the beginning of your talk with?
Thin manifold.
There's, like, that low-dimensional space that you want to sample from.
Yeah, so I mean, these methods, they empirically do discover that, right? So these are methods that are built to find the different metastable states of proteins. And it's like, there's a long history of, building coarse grain models showing that this is possible.
Coarse grain models still preserve the shape of the energy landscape to be able to find those states.
They do so enough that when we backmap and metropolize, we can recover the statistics correctly. But there is an important part of this, which is that because we're using methods where we can compute these posterior probabilities, we can reweight all of our samples relative to a target distribution. So as long as we're sampling in, like, approximately the right places, the results will be good. I think it's entirely conceivable that there are modes that will be missed. And a big part of the reason that we're focused on intrinsically disordered proteins is that they don't have as well-defined metastable states. It's something where this sort of dynamical sampling can give us a lot more information. Okay, great questions. Thank you. Keep them coming. Yeah.
Sorry for one more. On the coarse screening part, apologies if you said this, is that usually like Cartesian beads that essentially is representing, or is there other variables like orientation or?
No, so we're doing the most basic type that you can imagine. So, center of mass of the bead that we're coarse graining, projecting it down to this lower dimensional space. I mean, as I said, if you read that JCP paper that we first presented this in, we use a nonlinear embedding, and we've done a lot more testing on that since, and I'm just not entirely convinced that the nonlinearities actually help. Plus, for what I'm about to talk about, it's much easier if we have a shared coarse graining across all of structure space or all of sequence space. Okay, so we want to avoid doing MD on problem-specific examples. So one of the things that was actually pointed out to me by David Wales was that there are these gigantic libraries from the bioinformatics communities of rotameric states of side chains of peptides. And he was like, well, why aren't you just using those? And so I thought about it a little bit, and we took some of these rotamer libraries and we tried to train on them initially. And actually, they just didn't have very good overlap with what we see in MD, because they have a lot of crystal structure artifacts and other things that are kind of not relevant for a thermal distribution of proteins. But David had actually done some numerical work, so he's big into global optimization, as he calls it. And what he had done is basically try to enumerate all of the metastable states of tripeptides, small protein fragments. So we took a look at that data, and it was all an implicit solvent. Didn't like that either. But so we just made our own using MD simulations of tripeptide fragments in explicit solvent. And the project of building these rotamer libraries goes back initially to Ramachandran. And this was back when the PDB had about 35 structures or something. And they had made a simple prediction for the chi-1 dihedral angle of a side chain coming off the backbone. And basically what they asserted was that there aren't that many states that are energetically accessible to this side chain. And they, made some simple model of the side chain dihedrals, and looked at the Boltzmann weight of them, and they said that there are 3 states basically, and that compared well with the empirical observation. So indeed, it's true the distribution of an individual rotamer is relatively constrained by what is energetically accessible. And if you look at the types of distributions that you get, so now I'm showing you marginals in all their full glory of chi1, or so chi1 to chi10 of a histidine. And the point of this plot is basically to illustrate that the rotamer distributions depend very strongly on the sequence, even for something like a tripeptide fragment. So if we take one of these tripeptides and you look at the histidine moving around as it samples conformational space, you get these distributions where the angles are often simple multimodal distributions, so not that much structure to these distributions. But if you compare this to a protein where we're looking at a histidine in situ with different surrounding residues, some of the modes are changed rather dramatically. The variances change quite a bit as well. And so we need to somehow represent this sequence dependence. So what we did was we built extremely simple models of this. So these are multivariate von Mises mixtures. And so it's basically like the generalization of Gaussian mixture models to circular statistics. It's relatively straightforward to train these. I say with Stephen in the room, who spent a lot of time actually figuring out how to do EM on these mixture models. It's not trivial. There's like one paper that does it. And basically, what we're trying to do here is for each of these tripeptides, or each individual rotameric state, actually, we can fit a model which is just a mixture of means and variances of von Mises distributions, which are these unimodal circular statistics models. And we can train them with, this is hardly even machine learning, right? This is expectation maximization. So it's very, very straightforward to train these models, something that we can do quite quickly in comparison to training any other type of model. And the attraction of this is that we have like a very strong prior for individual side chain distributions in context on a larger protein. Of course, we can't just take the sequence of a protein, take a backbone structure, and attempt to backmap just using a product measure of all of these mixture distributions. That won't work because there's very, very strong correlations among all of the side chains. It's like a mini body quantum system in some sense, right? There's extremely long range and strong correlation among all of these different individual side chain distributions. So the idea is to do what everyone does now, right? You use a language model type architecture, right? We use attention to actually couple all of the side chain distributions. And this works extremely well because the structure of proteins, we already know, is reasonably well captured by correlations among the side chains, or among the residues along the sequence. And the attention mechanism can do a good job of attending to which modes should be populated given a backbone. And so that's the basic paradigm. So we're going to present the backbone without the dihedrals, without the side chains, to a transformer. We use a standard transformer. There's nothing really special about it. And what we predict, the readout in this like sequence to sequence problem, is that from the sequence of the structure, the internal coordinates of the backbone, we read out which modes and their populations in this mixture model. So we're basically instructing the model which of these mixture modes to sample. And so that corresponds very strongly to a given structure. There's, of course, still a distribution that we have to sample. And so maybe a little bit in a prettier schematic, it looks basically like this. So we have a backbone encoder and a rotamer decoder. And that decoder is a policy in the sense of like a language model policy that tells us which side chains to sample given a backbone. To maybe tell you a little bit more about how we train this. So it's a standard transformer, as I was saying, and there's a backbone and amino acid embedding. So this contains information about the specific dihedral structure of the backbone. and then also what type of amino acid it is, so that we know, what modes are available. And we pass this to our mixture components, and we train it with a simple energy cutoff filtering method. I'll talk more about how we train it, towards the end. And right away, on simple proteins, we see that if we sample the uncoupled model, we get strong steric clashes. If we sample the transformer-trained model, we avoid those steric clashes, and we actually get really good agreement with molecular dynamics on a lot of observables. It doesn't do so well on subtle hydrogen bonds. That's something that we're thinking a little bit more about how to fix. But the most interesting part for me is that it actually has the opposite problem of the normalizing flow. So when we build these models, they are over-representing the available modes for the protein structure. And that's something that we can correct with metropolization and with sort of reweighting strategies. But the transformer naively gives things that sample states that are not really populated in our MD simulations. Exactly, yeah. So if we look at the totally uncoupled mixture models, those will sample basically all of the available states for a given sidechain. The transformer, at least to the extent that we've trained them, doesn't patch it up fully. I think we're training these on much larger data sets now, and I think it probably will improve the performance a lot, but it doesn't patch it up fully. But that's actually not a problem, because there are strong statistical guarantees if we actually sample this in the right way. So with Mary Lou and also with Stephen, we've figured out strategies that we think work for metropolizing this sampling procedure. So then the underlying Boltzmann statistics will be reflected exactly, again, up to the resolution of our molecular dynamics energy function. Yeah. Well, I think it's primarily because the transformer is actually coupling, it's finding the submanifold of the underlying structure of the protein reasonably well. So we're not actually proposing, an exponential number of different mode combinations. Yeah, the transformer is predicting, strongly correlated sequences. You could pose exactly the same question about like ESM, right? Like, why does it not just predict, everything? It's because there's actually really strong constraints on the types of motifs that you see. And that's true here too. Like, there are modes that will just not be populated within a certain subsequence. So yeah, I'm confident that will not be a problem. And even if clearly you can reweight this to this. Yeah.
You basically weighting an energy twice, so I wanted to close the loop on what's happening with the solvent.
Okay, so this is a very, very good and important question. Yeah, so it's one thing that I would love to figure out. We are computing the energy in an implicit solvent. We do not backmap the solvent. I struggle to come up with examples where this is truly important to capture. I think if we improve the quality of implicit solvent models, we essentially fix this problem entirely. But it is a question that comes up constantly, like what do we do about the solvent? I don't have a good answer. I think increasingly we're looking at, building representations of the target distribution that incorporate both experimental and molecular dynamics information, or like force field based information. That may help also, but yeah, the solvent is implicit here.
So when you're metropolizing by the train time, it was explicit.
Yes, exactly. So the structures that we propose, so the prior does have information about explicit solvent. And so I think that that's also part of, and same with our coarse grain models, those are trained in explicit solvent. And so as a result, we expect the structures that we see to be reasonably reflective of the explicitly solvated distribution, but we do not know how to evaluate the energy in the explicit solvent. I've also thought about just training a model that actually tries to correct. I think that might be one way of getting around it, but yeah, I don't have a great answer to that question, but it's a really important problem. Yeah.
My question, what allows you to reweight it to get the correct distribution? Like, where's that information coming from?
So what we do, so we know how to compute this, the statistical weight of the CG distribution exactly. That's coming from our coarse grain potential. Transformers actually output probabilities directly, so that information we have. So we view this as a sort of lifted Monte Carlo method. So we're basically integrating out the degrees of freedom that we're sampling over. And this conditional distribution we can compute exactly because it's just the von Mises probabilities. So every probability in this generation is totally explicit. And so the only thing that we need to do is reweight. Is there one more? Yeah.
Oh, when you mentioned reweighting, is that something you think you can do like fine tuning to, or kind of absorb back into the transformer?
So very good question. I'm going to come to it. Yeah. Okay. So the last point that I'm going to make on this is basically that if we change the backbone, we capture the effects of the side chains well. So this is something that we've seen in this androgen receptor protein that I actually started with. So this is an intrinsically disordered domain, and as we change the backbone to have stronger or weaker helicity, the side chain distributions that we see along that region are well captured. So the last thing is that I really didn't say too much. I sort of glossed over it. How do we train this model? So the training paradigm here is basically to use what are becoming increasingly common strategies for training transformers, which is basically to use alignment type algorithms. So algorithms that are meant to try to optimize a policy to reflect a correct ranking statistic. So I'm going to say a lot more about this, but the basic idea of these algorithms is to look at pairwise comparisons between two different proposals. So we have one backbone. We look at two different structures. We actually, in this case, know the relative ranking of them exactly because they're Boltzmann statistics, right? So we can just look at that relative probability, and we train the model to try to be consistent with that probability. So initially, when we were thinking about this, we thought, well, there are these methods out there. There's PPO and DPO. Like, we'll just take the reinforcement learning from human feedback framework and just transfer it to this. But we quickly realized that that doesn't really work for a lot of different reasons. And that actually made us think about a sort of different strategy for doing this. It's one that we call energy rank alignment. And basically, the premise of this is that because we essentially know our reward model exactly, so we know the relative ranking of these two configurations that we would propose given some context, we can turn this into an optimization problem that allows us to approach a Boltzmann distribution. So energy rank alignment has the property that when we turn down the regularization of our reference policy, we end up with a distribution that is asymptotically close to the Boltzmann distribution, whereas DPO and PPO do not have that property. So the way that this works is it's actually really simple. We don't use reinforcement learning at all, so we don't use PPO. We instead optimize on an objective, which is just exploiting the fact that these pairwise comparisons, the distribution only contains two different probabilities, and so we can train on the DKL of that distribution directly. So we can try to match the policy to the expected ranking distribution exactly. And this is, so this is, provably giving the right answer in the limit that, so when we take gamma to 0, gamma is not written here, I put the wrong formula in. So gamma is the term that's proportional to the regularization property. And so if we take gamma to 0, which again, sorry, there should be a gamma here, that makes it exactly the Boltzmann distribution. And so we developed this to try to fix this issue, to get us back to an energy distribution that is exactly the thermal distribution that we want. But we realized that it's considerably more general. And so we started thinking about searching through chemical space using alignment strategies like this. And so one of the things that we did was we had a molecular transformer sitting around for a different project. And we started to ask, well, can we actually search through chemical space using these sorts of alignment strategies with simple reward models? So the idea is basically to try to align these molecular GPTs. So these are generative pre-trained transformers that are trained on SMILE strings that come from databases of molecules that you can purchase or molecules that people have synthesized. And the idea then is to sample a distribution, so a policy that produces these molecules, and guide it using reward models that are built with here simple objectives. So high ring count, high hydrophobicity, high quantitative estimate of drug likeness, so kind of standard, straightforward properties. And the amazing thing is that it works. It works reasonably well. So we can really shift the distribution of our search through molecular space. You can see the distributions of the examples that we generate under different alignment objectives. So typically what we're doing in these examples is we're taking, for example, a Gaussian distribution around some target value of refractivity or some target number of rings, and we're sampling a distribution with an energy function that is corresponding to the log of that Gaussian. So it shifts the distribution, as you can see, right? And we can kind of push it by tuning the temperature so that we get either more mode-seeking behavior or less mode-seeking behavior. But I think that one of the core points here is that we retain a lot of entropy in the objective because unlike the DPO objectives, our objectives are built to actually have the entropy directly in them. And so that part never goes away. We're always targeting a distribution which has an appreciable breadth to it, unless we take beta to infinity, right? Unless we set the temperature to 0. So it's a really controllable parameter. Yeah. We sample the pairs of Ys randomly. Yeah, I mean they're conditioned, or it's given a context. So in some of these examples there's no context, but in some it's prompted. And one aspect of it that's actually, I think, maybe the most surprising part of it is that if we look at the aligned models and we compare the Tanimoto similarity, which is basically a simple proxy for how similar two molecules are, we basically don't shift the distribution of similarities. So it's not like we're seeking some small number of motifs or like some small region of chemical space, which is typically what reinforcement learning does. Reinforcement learning pushes you towards a particular type of chemical. This actually retains the sort of statistics of the underlying distribution quite well. You can do it with multi-objective and with prompting. So this is a multi-energy alignment involving QED. We can prompt with molecules that, so that we retain, some overlap with the molecule that we started with. That seems to work reasonably well. We're looking for harder tests for this sort of thing. So, if there are suggestions, I'm very open to those. And the algorithm is truly general purpose. So, we can do actual large language model alignment with it. That seems to work pretty well even on what are sometimes called super alignment tasks. So this is basically aligning llama 2 13 billion with llama 7 billion chat, which is an aligned. So aligning an unaligned model with an aligned model. That's sort of thought to be one of the kind of frontier challenges for alignment. So how do you actually align things that are going to produce outputs that are too complicated for people to rank things directly? And the results are pretty encouraging and good. So like here's one of the types of prompts that you see in these harmful and helpful data sets. So you ask the GPT to do something illegal, and it's if you train with ERA, you get things that say don't do that, it's illegal. It's actually hard to do baselines in this space because everything is so computationally expensive. But our implementations of DPO gave mode collapse. So we've found the sort of mode-seeking behavior where it finds high reward token, which is a period evidently, and that's the output that we get. So I think one of the main points that I want to make about this sort of thinking about how to leverage large language models in a sort of chemical and sampling context is to really think about it as a kind of structured search. I don't think that this is a common way of thinking about LLMs, although maybe there's some things out there. But really, I think part of the power of LLMs is something that they're often derided for having, which is incredible information retrieval capabilities. And that's something that we can really leverage. And one of the contexts where we've looked at that a lot is in NMR. So in NMR, you make an experimental measurement of the resonance, the nuclear magnetic resonance. And this is H1 NMR, and we use also C13 NMR data. And what you would like to do from this data is predict which molecule among all of these is this NMR corresponding to. I don't know if we have any NMR savants in the room. Does anyone know which molecule this is? Can you read it? You probably can't even see the lines well enough. Oh, it's actually not the box isn't appearing. It's this one. And this is something that is really an increasingly difficult problem as the molecules get larger. So for very small molecules, it's actually easy to assign the peaks, and organic chemists are extremely good at this. It's actually amazing to watch them do it in real time. But I am not good at this, and so we've thought about how to automate this problem. It was originally Matt Cannon, my colleague, and Tom Markland who were thinking about how can we use machine learning in this context to make predictions of NMR. And what I suggested was basically, well, you should be using transformers somewhere in this. And basically, as the problem size increases, the space over which you would need to search becomes extremely, extremely large. So chemical space grows very, very rapidly. And they had a methodology for doing this that was basically using a beam search at the last step. And that's not something that's scalable. So they could go to about 11 heavy atoms. And so we thought about architectures that would allow us to get to all of the, say, 10 to the 12 possibilities for like reasonably sized compounds. And the basic premise is to build an architecture that can identify the meaningful substructure. So it sort of emulates the way that humans think about NMR. So we usually look for functional groups and try to identify the motifs that are kind of relevant for making a prediction. And so the first part of this is sort of a classical machine learning task in the sense that we have a CNN that's just trying to identify which substructures should be predicted given the input NMR. And then we couple those substructure predictions to a transformer, which then tries to predict which chemical formula do those substructures correspond to. So the substructures, we worked with an organic chemist to come up with the set of substructures. There are 957 of them for some reason. Those are like all the functional groups that they thought were important. And we use that to build an embedding that we feed into this model, which then takes, uses, again, a sort of standard transformer architecture to do this sort of multitask problem of predicting the SMILE string given the substructures. Okay, so this is something that basically automates structure elucidation, or at least provides good suggestions. So you'll see that the accuracy is not like insanely high. If we look at the test set accuracy, it's like 65%, but we've also identified the set of meaningful substructures. So that's something that ends up being extremely useful. Actually, that's the bottleneck in our methodology. We can go from the substructure, exact substructures to the correct molecule with more like 95% accuracy. It's just that the prediction of the substructures is still not perfect. And when we use H1 and C13 NMR together, this is something that works really robustly. And in fact, it scales to problem sizes that are now in the trillions of molecules, right, with a loss of accuracy that is pretty modest, I would say. And like this is something a bit like what was suggested earlier, where you could sample many different molecules, do the forward prediction task, which is easy, and compare to the NMR that you've obtained. So it's something that can really help automate the interpretation of these NMR data, which are very tedious to interpret. And I do think that that's kind of a good framing for maybe one of the ways in which we can use transformers more like a search tool and less as like an AI. So there are a lot of great questions. Thanks. I'm happy to answer more. This was done primarily with Abby, Sebastian, and Stephen, Stephen and Sebastian are here today, and Sriram, and then Frank is not pictured. He's a student with Tom. And thank you.
Yeah, sorry to keep harping on this. Have you done like an analysis? Sorry to keep harping on this. Have you done an analysis, and perhaps it's just obvious in your field, of this coarse grain potential function, how close it gets to those metastable? I get the name.
Yeah, so there's a lot of work on this in the field. So I would say most of it is not really looking at transferable models. It's primarily looking at one protein at a time. But with reasonable sampling of the conformational space and with reasonable training, you can get things that are almost quantitative on the free energy. So what the coarse grain potential is trying to represent is the potential of mean force. So it's the marginal distribution with the constraint that all of the integrated out degrees of freedom, are mapped to so it differs by a constant from, the true free energy. That's something that you can approach very, very closely in system-specific coarse graining. There's a lot of recent work on transferable coarse graining, and I'd say the results are very, very encouraging, but I don't think that there's a precise answer to the question, but it's something that asymptotically you could approach with the correct amount of data. It's not unlearnable. Yeah.
Thanks for the great talk. So I love the NMR stuff at the end, and I think about mass spec in the same way. I'd love to see more work in that area. Have you talked to chemists about like combinations of experiments that would be most useful in this context? With NMR we have lots of NOE, COSY, lots of experiments that can provide additional types of information. Is there like a combination of experiments and models that would be much more generalizable?
Yeah, so that's a very good question. We haven't really done any sort of we haven't even really thought about doing like targeted experimental campaigns to try to generate data for this problem. Matt, who is the experimentalist on the project, his group has done a lot of NMR on like predictions that we've made, and also like diagnosing things that aren't predicted correctly. But I do think that there's obviously an opportunity to do something at a much larger scale, trying to choose molecules that are somehow anomalous or have rare functional groups, things like that. But yeah, it's not something we've given a lot of thought to, but it would yeah. So if someone wants to give us money to do that, I would be very, very happy to do it.
For the part of the modeling where you had the mixture of Mises, I don't know Mises very well. Is there any generalization where you could sort of have it more complex, like two positions, if you will, distribution, so that when you're stringing together, you need to kind of compensate less? Or is it?
Yeah.
You're thinking of, and also in the same vein, like you fix those models and then you put the transformer on the top. You could imagine like actually revisiting some of those parameters, but I'm guessing in the case you have now, that's probably not worthwhile. But
yeah, so it's a good question and an interesting question. I mean, obviously, the best that you could do would be to train on like larger sequences, right? Like, so there's a trade-off here between how compact can we make the representation versus how much context do we actually need to make accurate predictions. I think that the way in which we see deviations from the product measure in the context of a real protein is actually basically through mode deletion. So there are modes that are removed when there's say like another amino acid in the way. And that sort of thing, I think, is actually fairly easy to represent from the types of distributions that we have. So, Stephen has done some work trying to analyze, what happens when we compare the tripeptides to proteins in the CATH database. And I think increasingly we're actually going the opposite direction. We're going down from tripeptides to just the individual amino acids, because that way, we can get all of the mode structure that is available like across all of sequence space, and then just selectively train the transformer to ablate them when it needs to. So yeah, my work on normalizing flows has led me to try to build models that have too many modes, not too few, and that's kind of the design principle that underlies the strategy. Yeah.
I just have a question about the NMR. That's really something that's very interesting for us, like experimentalists. It's a bottleneck for characterization. But what is the task you're really asking? Like, given the spectra, what is the molecule, or do you input more information? Like
just it's the H1 NMR and the C13 NMR. That's it, and then we predict the molecule.
Because like in a practical case, we have much more information than that.
So yeah, of course, right? I mean, you can definitely do better than if you have additional information. So yeah, these are like, it's meant to be as general as possible and for as routine, small molecule NMR as possible. But if you know what the like reactants in a reaction are, right, then obviously you can constrain the search space even more. It's the data that we have available for this is a mixture of experimental and computational data. And that data usually only lists the molecule and the NMR. We don't necessarily know the provenance of the molecule. I mean, there are ways of imagining trying to extend this to have some sort of reaction prediction type thing, but I think there are many interesting things that you could potentially do with it. This is the simplest version of it. Yeah.
There's no.
One more. Yeah. One.
The mixed discrete like 1BC is kind of struggle to was really cool from bitter experience, right? That's triangles. I think you mentioned at some point that maybe distal side chain interactions like hydrogen bonds were still like challenges there, and I forget if you said you had like thoughts around this. Or...
Yeah, so the first version of it that we did, which did not have the energy rank alignment at all, does have those problems. I think that there's probably some hope that we can generically correct it with just that level of intervention. There's more that you could do. I mean, we don't do any sort of like energetic relaxation at the end. That would likely help quite a bit. It's just that, each additional type of move that we add makes the Monte Carlo interpretation more difficult. I think if we get something that, where we're close enough to a Boltzmann distribution that we can start decorating it a little bit more and not worry so much about destroying, the physicality of the distribution that we sample, then we're willing to explore those sorts of directions. But for now, I think, the mentality is to make things as metropolizable as possible. Yeah.
Great. In that case, we'll go ahead and